All right. So as you'll recall, the girls were getting worried about Bessie because they were concerned about temperature. Okay? We needed to understand how was the temperature going to change the formation of the nitrogen. How does temperature change the rate at which the chemical reaction takes place? Okay? We wanted to know that. Oh, it's too high. I see what you're saying now. I thought you were making some sort of weird. There we go. No, Bessie is the cow. Bessie is the cow. So, we need to understand a little more deeply how the equilibrium or the rate constant K is controlled. What aspects of the collision are controlled by that K value? We know how concentration changes all this stuff. We can look at concentration versus time. We can look at rate versus concentration. And both of them have that K value in there. In that K value is a lot of important details around how the reactions happen. How do collisions control chemical reactions? And what controls those collisions? We already know some of this stuff. We've talked about the temperature of the chemical reaction. The higher the temperature, the faster the particles are moving. They're going to hit each other more often. They're going to hit each other harder. Okay? Those are things that we need to quantify now. We want to go through and we want to talk about how does the process of two molecules colliding and reacting, how is that controlled? What variables, what factors change whether a collision will create a reaction or not? Okay? So, number one, activation energy. Two particles collide doesn't mean that a chemical reaction happens. Not all collisions result in effective reactions. One of the big things we have to think about is during that chemical reaction, we have to break some bonds. If we had, for instance, this bromine, nitrogen, oxygen compound, if I had two of those molecules, and they're going to react together. Okay, so for the reaction to take place, the two molecules have to collide. Okay, the two molecules have to collide for that chemical reaction to take place. Notice when they collided, there was a next sort of thing. The nitrogen-bromine bond started to stretch apart. Okay? And it is once that stretching starts to take place that the bromine-bromines can move together and the nitrogen-bromine bond can break. Notice we had to break that nitrogen-bromine bond. It had to be broken apart. That takes energy. The energy to do that comes from the collision. So the particles have to collide, they have to hit with enough energy to pull that bond apart. We frequently like to take and graph this information. We want to show a graph, a display of the potential energy, the chemical potential energy, the energy stored in the bonds. Okay? Here we have our reactants, two separate molecules. They come together. That kinetic energy that they have when they hit together is transferred into potential energy that stretches that nitrogen-bromine bond and forms what we call a transition or an activated complex. This is that weird molecule we saw in the middle where the bromines and bromines were starting to bond together and the nitrogen bromines were starting to stretch apart but hadn't broken all the way. That's the transition complex. That's the activated complex, okay, the transition state, where we're in this weird in-between, very unstable state. There are two things that could happen. The molecules can bounce apart okay, and slide back down to the reactants. Or if there's enough activation energy and things are right, just right, they can break apart and form new compounds. The bromine-bromine bond can form, the nitrogen-bromine bond will break, and we'll get these new products formed. This, okay, reaction coordinate diagram shows the energy at the start, the energy of the activated complex, the transition state, and the energy of the products. We've already done some work with this information, you just don't realize it. The difference in energy between the reactants and the products is the delta H. The difference in energy between the reactants and the products is the enthalpy, the amount of energy absorbed or released by the chemical reaction. So this value right here, you can see here that the products have less energy than the reactants. Would this reaction be exothermic? Would it give off energy? Or would it be endothermic, take in energy? So why do you think it's exo? Less energy afterwards means that the net has to give off energy. Energy has to be released. What if it was endothermic? What would be different about this graph? The products would end higher than the reactants. They would have to absorb energy, gaining energy, and the products would end higher than the reactants. Okay, so we have this activation energy, the difference between the reactants and the activated complex. This value right here is what we call the activation energy. How much energy do the reactants need? How much energy does the collision have to supply to form that transition state? Okay? The greater the activation energy, the less likely any one collision is to be effective to form a chemical reaction. The temperature changes the percentage of collisions that are effective, that form a reaction. When I look at a graph, a distribution of the particle energy, okay, this is the energy that the collisions have versus the number of collisions at two different temperatures, temperature 1 and temperature 2. This line right here, this point right here represents the activation energy. Collisions to the right of this point have enough energy during their collision process. There's enough kinetic energy from that collision to meet the activation energy requirement to form the transition complex, the activation complex. Okay? So, as you increase the temperature, second T2 is higher, you can see that a greater number, a bigger area, is colored in. A greater percentage, a higher percentage of the collisions have enough energy because more collisions are happening with more energy. They're harder collisions as the temperature goes up and the particles start to move faster. Okay? Lower temperatures, notice, right, the lower temperature, lower percentage of collisions have enough energy. We can explain this, we can represent this with math. The y-axis is number of collisions. Number of collisions here. And this is the collision energy. So, mathematically, the number of collisions with the activation energy is equal to the total number of collisions times this factor. This activation energy factor is E, which is a number. Remember, E is the natural number, E 2.3 something or other. So E raised to the negative activation energy divided by RT. R is the universal gas constant in joules, 8.3145. T is the temperature in kelvins. R 8.3145, that's the universal gas constant expressed in joules. EA, this is EA, that's one, It's E sub A, so it's 1. That's the activation energy in joules. Temperature in Kelvin. N sub A is the number of collisions that have the activation energy. N sub T is the total number of collisions.
Wait, well the...
Hold on.
Is NA the number of collisions that end up causing an reaction?
Maybe. Sort of. Almost. There are other factors. It turns out that the number of effective collisions is actually way lower than the number of collisions that have enough energy. There's got to be some other factors involved here.
So what is NA?
N sub A is the number of collisions that have the activation energy for the reaction. That have enough energy that they could form a reaction based on some other factors I'm going to talk about in a sec. So that's the next slide. If you want to know what it is, look on your notes and look at the next section.
Are you talking about enough energy it takes to break the NO bond?
Well, it would be the NBr bond, but yeah.
Oh yeah, the NBR bond. Wouldn't you also get some energy from...
Right, you get some energy back out from the formation of the bromine bond, absolutely. But that energy is not, it's complicated because it's all happening at once, right? So it's a combination of they have to be some to get it started. Then you can get some going. It really, at the micro scale, this is quite a bit more complex than we're doing it, but at the macro scale, this works really well. The useful equation sheet doesn't have this exact formula because this is sort of an intermediate part of a larger formula that we're working towards. But it does have the overall formula I'm going to teach you called the Arrhenius equation. R is 8.3145, which is the same value, but in joules. In joules, that's in atmosphere liters per mole Kelvin. This is R as joules per mole Kelvin. Pretty much you only use that atmosphere liter value when you're dealing with the ideal gas law. Otherwise, it's the 8.3145. Again, that's on the useful equation sheet, right? Both of those values are on the useful equation sheet with their units listed. So if I increase the temperature, what happens to this value, this E to some number value? It becomes this is a multiplier. So what would we expect about the number of collisions? We would expect it to go higher. So this value becomes either, if it's less than 1, it becomes closer to 1. Because this is value, you can't have more collisions with energy than collisions that you have. So this is some number less than 1. But it becomes closer to 1 as temperature increases. Okay? Now, we have just said, well, wait a minute, how come all of these collisions don't work? And that is because there are other factors involved. What we call sterics. Sterics is the orientation in space. Okay? Sterics is the study of orientation in space for molecules. Remember when we looked at this reaction? We said, hey, bromine, nitrogen, oxygen, if they collide like this, the two molecules come together, the bromines can interact, stretch this bond. Okay? If they collide with enough energy, this bond can completely split apart. The bromines will squish back together and form new bonds. We've got our chemical reaction. Okay? Now, what if, however, they collided together, but not in that flat, straight up orientation? What if they were collide like this? What if they bounce off the two oxygen molecules? Right? Maybe we could have a different reaction. That's possible. But in this case, let's say that doesn't happen. Are the bromines close enough to interact with each other? Not even a little bit. This reaction is just going to bounce right back apart. So, even if we have a collision with enough energy, the orientation in space, the sterics, have to be right for the reaction to take place. So our total number of collisions has to be modified by some frequency factor that describes what percentage of the collisions have the correct orientation in space, have the correct sterics. So, our rate constant K can be described as the product of the frequency of the collisions, Z. Z is the frequency of the collisions. P, the steric factor, the percentage of collisions that have the correct orientation, times the e to the negative RT, which gives us the percentage of collisions that have the correct amount of activation energy. Hey.
Can you make a quick announcement about a wind drive?
You may. We'll deal with it. You can throw a change in there in a little bit. Yes? So, K is our rate constant, like we've been using in our rate laws. Z, frequency of collisions. P, the percentage of collisions that have the correct orientation. And then this whole factor, e to the negative EA over RT, that's the activation energy factor. That's the percentage of collisions that have the activation energy. Question?
What would be the units on
They're going to be, yeah, they're going to be sort of like collisions per time unit. Z is going to be collisions per time unit. This is going to be a dimensionless number, fraction.
And if it was like 50% and the rest 50 or
0.5. They're going to be fractions. So, now what we do is it is very common to combine Z and P together for a reaction into A, what we call the Arrhenius factor. So A is the Arrhenius factor. And then it is even more common to rearrange this equation so that we get these variables, the temperature and the activation energy, out of the exponent. And we do that using natural logs. And so I'm just going to, you're going to trust me that mathematically this is doable. If you're in Algebra 2 or you've taken Algebra 2, you should be able to do it and take this equation and turn it into this equation. All I did was use some natural log magic to get this stuff out of the exponent and get it into that form. Does the form of this equation look familiar to anybody? It's the same form we use for almost every equation in this class. Y equals mx plus b. This is the equation for a straight line. If you graph the natural log of the rate constant versus the inverse of temperature, the slope of that line will give you your activation energy. We can find out the activation energy of a chemical reaction by studying its rates at different temperatures and seeing how the rate constant K varies. Oh my gosh, I wonder if we'll have to do that as part of our lab. I bet we will. So this equation is on the useful equation sheet. Okay, that equation is on the useful equation sheet. What does that mean? That means we have to know how to use it because, while unlikely, it is possible that they will ask us questions that require us to actually do calculations with this equation. Okay? It has not happened in a long time, but since it's still on the useful equation sheet, we definitely need to understand it. And we're going to do a couple of problems that involve it, homework problems, and our lab is going to ask you to use this equation as well. We're going to take a chemical reaction and we're going to determine its rate law, the rate constant, then we're going to do the rate constant at different temperatures so that we can get the activation energy for the chemical reaction. I know you're all very excited about that. It's fun lab. It's good. You get to use stopwatches. See, now that's the reaction I'm looking for, stopwatches. All right. Here's the thing, though. No fire. When it's cold, what happens to the rate of the chemical reaction? goes down, particles move slower, fewer percentage have enough kinetic energy, right, to reach the activation energy point. Yeah, I frequently have poor grammar. What about when it is cold? Is there any way we could speed up the reaction? See, that's what it says. It should say, what about when it's cold? Question mark. Capital I. Is there any way we could speed up the reaction? Wow. I should probably have my wife check these things out before I do this. All right, okay. Hold on just a sec. How's that? Is that right?
Yeah.
All right.
Did you talk about catalysis yet? Previously. Okay. I just have a question about what you mean when you call it acid structure. I don't understand the grammar.
That happens a lot too.
Catalysis lower the activation energy by changing the activation.
All right. Okay. All right. So we can change the rate constant K without changing the temperature. But to do it, we have to change how the chemical reaction takes place. Okay? We have to change what we call the reaction pathway. That's what a catalyst does. A catalyst is a substance that provides usually some sort of surface support for the reaction to take place on. And what it does is it changes how the chemical reaction happens. And that effect of changing how it happens is to lower the activation energy. Catalysts, by definition, are not used up in the chemical reaction. They literally provide a support for the reaction to take place. In biology, proteins, right, very large macromolecules do this all the time. That is what they do. That's what they call enzymes. Enzymes are biological catalysts that have evolved to help certain chemical reactions take place. There are lots of other types of catalysts. In industry, we typically use metal surfaces. So metals, because of their crystal structure, can frequently provide a place for chemical reactions to happen, to change how they happen, to provide support, reducing the energy required to reach the activated complex. Okay? So catalysts speed up chemical reactions by lowering the activation energy, which they do by changing how the reaction happens. They have to change the reaction pathway. So for instance, hydrogen peroxide this reaction can be catalyzed, okay, by adding manganese dioxide. And I would do a little demo here. It's really exciting. But we don't have any hydrogen peroxide. And you need concentrated hydrogen peroxide for it to work. I'm sorry. Well, we don't have any at the school right now. I forgot to order some. I should order some for next year. Thing is, it doesn't store very well.
You should order some just specifically for this class.
Okay. It'll probably come in a couple of months. Yeah, except that instead of the 3% hydrogen peroxide you buy at the store, we need like 30% hydrogen peroxide, which can be used as rocket fuel. So yeah, you can't just go down to the store and pick up a bottle. You have to order it special, and it doesn't store very well. So it kind of needs to be fresh. It would be bad. It would hurt. It breaks down. It breaks down into water and oxygen. I mean, it's not a very stable compound. The activation energy is fairly low. If you don't store it, if you store it in heat or light, it just doesn't store very well. So, catalysts are the solution to speeding up reactions at lower temperatures or even they speed them up no matter what because they drop the activation energy.
What's the activated complex?
The activated complex is that transition point. It's that point in the middle where the molecule comes together but hasn't yet formed the new compounds. That's where we have to get to form that's what the activation energy gets us to. Gets us to the activated complex or the intermediate. Okay? So, 3 things we worry about, 3 things we think about when we're talking about the rate constant. Okay? And how can we control the rate of a reaction without changing the concentration? We talk about the activation energy. How much energy does it take? We talk about the temperature, okay? Because increasing the temperature increases the number of collisions, the percentage of collisions that have enough energy. We talk about the sterics, the orientation in space. And changing the sterics, which is really, that's what the nature of the chemical reaction, the nature of the molecules involved. And then the other thing we talked about was catalysts. Catalysts change how the chemical reaction happens. They change the pathway, lowering the activation energy.
That's a list of ways to affect the rate of reaction.
That's a list of ways to, affect the rate of reaction without changing the concentration. Okay? So it looks like we have pretty good control over these chemical reactions now. But the last thing we need to understand is why does all this work? How, in more detail, why do these things work? Because we know that we can go in the lab and we can measure these things. We want to have a theoretical underpinning, a theoretical understanding of how chemical reactions take place. Okay?